right now we actually have these high-definition 3D maps of the craters on Mars,
Right.
which is, a dead, frozen rock over 100 million miles away. We have rovers analyzing its dust, satellites mapping out the valleys. But if you look at the floor of our own oceans right here on Earth.
It's mostly just a blank void.
Exactly. I mean, we have mapped the surface of Mars in far greater detail than the bottom of our own planet.
Yeah, it is a pretty staggering reality check. And, it all really comes down to the brutal physics of seawater.
How so?
Well, when you want to map a planet like Mars or Venus, you just put a satellite in orbit. You use electromagnetic waves like radar or lasers to take these incredibly high-resolution images right through the vacuum of space.
Right, because space is empty.
Exactly. But try pointing those same orbital instruments at the Pacific Ocean, and you hit a literal wall.
Because water just swallows electromagnetic waves.
Precisely. Yeah, light and radio waves just do not travel far through water. They scatter and absorb almost immediately.
Oh, wow. So you just get nothing back?
Pretty much nothing. So to map the seafloor properly, you can't just snap a picture from space. You actually have to send a physical ship, equip it with multi-beam sonar, which uses sound waves instead of light, and painstakingly drive that ship back and forth across the surface.
Like mowing the lawn.
Exactly like mowing the lawn, but across every single square kilometer.
Which is just, an unfathomable task when you realize the ocean covers 70% of the Earth's surface.
Yeah, no, it's massive. Even with modern international initiatives trying to speed things up, a huge fraction of the seafloor has just simply never been pinged by sonar.
And I guess that gap in our maps represents a massive blind spot in human knowledge, right? Because the ocean isn't just a flat surface we sail cargo ships across.
Not at all. It's a massive three-dimensional living space. It provides the overwhelming majority of our planet's habitable volume.
And that, right there, is the ultimate mission for this deep dive. For you listening, we are heading down into that overwhelming majority of Earth's living space. We're going to explore a realm that operates under entirely different rules of physics, chemistry, and biology.
And we'll figure out why our dry, sunlit lives on land completely depend on what happens in the pitch black.
I love it. So to appreciate what is down there, we probably first need to define the territory, right? And the physical barriers keeping us out.
Yeah, definitely. So we generally define the deep ocean as anything below about 200 meters.
200 meters, okay.
Yeah, that's the twilight boundary where sunlight becomes just too faint for photosynthesis.
So the solar power plant shuts down entirely and it just keeps dropping from there.
Right. The average depth of the ocean is around 3,700 meters. And if you go to the Mariana Trench, down to Challenger Deep, you are looking at a drop of nearly 11 kilometers.
11 kilometers. You could take Mount Everest, drop it into that trench, and you would still have, roughly 2 kilometers of water resting on top of the summit?
Yeah, roughly 2 kilometers. The scale is dizzying. But the true physical challenge of going down that far isn't just the distance, it's the immense pressure.
Oh, right. The weight of the water.
Exactly. For every 10 meters you descend, the weight of the water column above you increases the pressure by roughly 1 atmosphere.
So by the time you reach the bottom of Challenger Deep, you're under roughly 1,100 atmospheres.
Yeah. And to put that in perspective, imagine a small car just balanced on your thumb.
Oh, wait. An entire car on my thumb.
An entire car. That is the equivalent crushing force pressing on every single square centimeter of space down there.
Oh, my God.
Yeah. This is why deep-sea submersibles are engineered with these immensely thick titanium spheres and why we rely so heavily on remotely operated underwater drones. Sending humans into that environment is just an engineering nightmare.
Right, which makes total sense. I understand why titanium works.
Yeah.
But this actually brings up a biological contradiction that genuinely confused me during our research.
Oh, about the fish.
Yes. If a heavily engineered submarine can implode under that force, how on earth does a squishy fish survive? Why doesn't an octopus just get turned into a pancake?
It's a great question, and it's all about what they lack. Pressure is primarily destructive to spaces filled with gas.
Okay.
So if you take an empty sealed plastic water bottle and dive into a pool, the pressure squeezes the air inside, crumpling the plastic.
Ah, right. But if I fill that water bottle completely to the brim with water and screw the cap on tight, I can take it as deep as I want. The bottle won't change shape because liquids don't really compress.
That is the exact mechanism. Deep-sea organisms do not have gas-filled spaces.
No air at all.
None. Shallow water fish often use a swim bladder, which is like an internal gas balloon to control their buoyancy, but deep-sea animals have entirely abandoned that evolutionary strategy.
Wow. So what are they made of then?
Their bodies are constructed mostly of water, lipids, and solid tissues. Because those materials are largely incompressible, the internal pressure of the fish naturally equalizes with the immense external pressure.
So there's just no empty space to crush.
Exactly.
But wait, doesn't that extreme pressure mess with their actual biology at a microscopic level? I mean, beyond just squishing them.
Oh, it does, and they have adapted to it beautifully. Deep-sea creatures have these unique cellular membranes and specialized proteins that maintain their structural integrity under forces that would literally twist and deform the proteins in our own bodies.
So they are biochemically engineered for the crush.
They really are.
Which, completely explains the tragic misunderstanding of the blobfish.
Oh, poor blobfish.
Right. I mean, it constantly gets voted the world's ugliest animal because those viral photos show it looking like a droopy, miserable pile of pink jelly.
It is a deeply unfair reputation.
Yeah.
I mean, you are looking at a creature that has been violently dragged up thousands of meters to the surface. It is suffering catastrophic decompression damage.
It's expanding.
Yeah, down at its natural depth under all that pressure, a blobfish looks like a perfectly ordinary, structurally sound fish.
So taking a blobfish to the surface is basically like taking a human and suddenly dropping them into the vacuum of space.
Pretty much.
We wouldn't look our best either. So, okay, they survived the pressure perfectly well, but they still live in absolute darkness. I mean, below 1 kilometer, no sunlight penetrates at all.
None.
So how do they find food or mates if they literally can't see anything?
Well, that is the beautiful paradox of the deep sea. It is completely isolated from the sun, but it's not dark.
Wait, it's not.
Not at all. It is heavily illuminated by bioluminescence. So living organisms creating their own light through internal chemical reactions.
Wow. Yeah, we found estimates suggesting that the vast majority of deep-sea species can produce light, which is wild because that makes bioluminescence arguably the most common form of communication on the planet.
It absolutely is.
But I have to challenge this logic for a second. Right. If I am a small, vulnerable fish in an ocean full of predators, turning on a bright biological flashlight seems like a terrible idea. Aren't you just putting a neon eat me sign on your own back?
It sounds like it, right? But it is an incredibly high-stakes visual arms race, and context is everything. You only use light when it gives you a distinct tactical advantage.
Okay, give me an example.
Well, the anglerfish, for example, uses it offensively. It dangles a glowing bioluminescent lure in front of its massive jaws.
Oh, right, like a fishing pole.
Exactly. A smaller fish sees a faint glowing dot, thinks it might be something to eat, swims over, and just walks right into a trap.
Ouch. So that's hunting. But what about defense?
Think about a squid. In shallow water, a squid shoots a cloud of dark ink to blind a predator.
Right.
But in the pitch black of the deep ocean, dark ink does nothing. So instead, certain deep-sea squid eject a thick, luminous cloud of glowing biomatter to temporarily blind and disorient their predator while the squid jets away into the darkness.
Are you kidding? It's literally a biological flashbang.
It really is.
That is brilliant. But my absolute favorite strategy we came across in the research is using light to hide.
Counter-illumination.
Yes. It sounds deeply counterintuitive, but it is a masterpiece of evolution.
It really is. So in the upper ranges of the deep sea, the twilight zone, there is a highly diluted, incredibly faint blue light filtering down from the surface.
Okay, so if a fish is swimming through that twilight zone, a predator looking up from below would see the fish's dark silhouette blocking that faint surface light, right?
Exactly. The shadow is what gets you killed. So these animals have evolved specialized light-producing organs on their undersides.
On their bellies.
Right. They carefully modulate the intensity and color of their belly lights to perfectly match the dim light coming from the surface.
They're so smart.
By doing this, they effectively erase their own silhouette from anything looking up. They render themselves invisible.
And if the camouflage fails, there's always the burglar alarm strategy.
Oh, yeah. The burglar alarm is great.
I love this one. If a small, glowing jellyfish gets grabbed by a crab and it can't fight back, it just flashes all of its lights as violently as possible, basically screaming into the void, hoping to attract an even bigger predator to come and eat the crab.
Yeah, the enemy of my enemy is a very convenient distraction.
Exactly. But all this flashing, hunting, and fleeing implies these animals have a lot of energy to burn. And we established that without sunlight, there are no plants. There's no photosynthesis at the base of the food web.
Right.
So what is this vast glowing ecosystem actually eating?
Well, food scarcity is the defining constraint of the deep ocean. Because they cannot harvest energy from the sun, nearly all life down there relies on gravity.
Gravity.
They eat what falls from above. Scientists call it marine snow.
Okay, marine snow. It sounds incredibly poetic until you learn what it's actually made of.
Yeah, it's not so poetic then. Marine snow is a slow, endless, drifting shower of dead plankton, shed skin, fecal matter, and decaying organic debris.
It's just falling from the vibrant shallow waters down into the abyss.
Yes, it is literally a rain of leftovers and waste.
And that sounds like a starvation diet. I mean, how do you build an entire ecosystem on such a sparse food source?
By drastically slowing down the pace of life, most deep-sea animals have incredibly slow metabolisms.
Right.
They move lethargically to conserve energy, they grow very slowly, and they can live for centuries.
Wow. And I guess when a meal does drift by, you just cannot afford to miss it.
No.
Which explains the terrifying anatomy of things like the gulper eel. I mean, you see these fish with unhinged jaws and stomachs that can expand to hold prey larger than they are.
Yeah, you eat whatever you can fit in your mouth, because you just don't know if you'll see food again for months.
Right.
But occasionally they do hit the jackpot. If something massive dies at the surface, like a whale, the carcass will eventually sink all the way to the sea floor.
Oh, whale fall.
Exactly. A whale fall creates an instant, massive influx of energy. It spawns a localized, highly active ecosystem that can persist for decades. You get different waves of scavengers, bone-eating worms, and bacteria systematically breaking down the carcass.
So for a very long time, marine biology operated on the assumption that all life in the deep sea was this, trickle-down economy completely dependent on the sun.
Yes.
Whether it was falling plankton or a dead whale, the original energy source was always solar. But then came the 1977 Galapagos Rift expedition.
Oh, yeah, which completely broke that paradigm.
Yeah, we have to talk about this.
It remains one of the most profound biological discoveries in human history. Researchers were surveying the ocean floor and they stumbled upon hydrothermal vents.
And what are those exactly?
They are essentially deep-sea geysers. Icy seawater seeps down through fissures in the Earth's crust. It interacts with scorching hot volcanic magma and then violently jets back out into the ocean.
And this water is loaded with dissolved minerals, and it is superheated, right? Like some of these vents, known as black smokers, are blasting out water that exceeds 300 degrees Celsius.
They are.
Wait, 300 degrees is triple the boiling point of water. How is it not just turning into a massive steam explosion down there?
Because of that crushing pressure we discussed earlier.
Oh, right, the weight.
Yeah, the weight of the water column physically prevents the water molecules from expanding into a gas. It remains a superheated, highly toxic liquid.
That is insane.
But honestly, the temperature wasn't the biggest shock. It was the life crowded around it.
Right, they found these dense, thriving alien landscapes down there. Meter-long tube worms with bright red tips, massive clusters of pale clams, blind crabs, basically an entire ecosystem clustered around boiling, toxic geysers.
And the mind-bending reality is that nothing in this ecosystem relies on the sun.
Nothing at all.
Nothing. The base of the food web here isn't a plant performing photosynthesis. It is bacteria performing chemosynthesis.
And this is the mechanic that changes everything, right? Instead of using light to create food, these bacteria extract chemical energy directly from hydrogen sulfide.
Exactly. A compound that smells like rotten eggs and is lethal to most terrestrial life.
Lethal to us, but they use that chemical energy to produce organic matter. They're literally eating toxic volcanic soup.
They are. And the surrounding animals have evolved astonishing ways to harness this. Take those giant tube worms you mentioned.
Yeah.
They are complex animals, but they don't have mouths, they don't have stomachs, and they don't have a digestive tract.
Wait, so how do they eat?
They don't, at least not in any traditional sense. The worms house massive colonies of these chemosynthetic bacteria deep inside their own tissues.
Wow. Inside them.
Yeah. The worms' red plumes absorb hydrogen sulfide and oxygen directly from the seawater and deliver it to the bacteria. The bacteria process the toxic chemicals into usable carbon compounds, and the worm simply absorbs what the bacteria produce.
It is a flawlessly integrated biological partnership.
It truly is.
It is just wild to think about. I mean, we are constantly looking for alien life in space, but the blueprint for alien life is just sitting at the bottom of the Pacific.
Well, that is exactly how astrobiologists view it. Proving that life can thrive independently of a star drastically altered the search for extraterrestrial life.
Because it opens up so many possibilities.
Absolutely. We know that icy moons in our solar system, like Jupiter's Europa and Saturn's Enceladus, have these deep, liquid saltwater oceans trapped beneath their frozen crusts.
And scientists believe those moons likely have volcanic activity at their rocky cores, right?
Meaning they almost certainly have hydrothermal vents.
Oh, wow.
Yeah. If life on Earth can flourish around hot rocks and chemicals and total darkness, those moons are now prime targets for discovering biological life beyond our planet.
That is incredible.
And furthermore, these vents are now a leading theory for where life on Earth originally began. They provide the heat, the mineral catalysts, and the protection from a harsh, radiation-bombarded early atmosphere.
So we have biological flashbangs, underwater volcanic food webs, and potentially the origins of life itself. It is endlessly fascinating.
It really is.
But I want to pivot to something more immediate. For you listening, maybe you live hundreds of miles inland. You maybe never think about the ocean. But this bizarre, extreme environment is actually dictating the weather outside your front door right now, isn't it?
Without question. The deep ocean is the unsung hero, the giant atmospheric regulator of our climate system. First off, it's an enormous heat sink.
Okay, a heat sink.
Over the last century, human activity has trapped vast amounts of excess heat in the atmosphere. The ocean has quietly absorbed over 90% of that excess heat.
Over 90%. So if the ocean wasn't acting as a planetary thermal shield, the surface temperatures we experience on land would already be radically higher.
Oh, unlivably higher. But the ocean doesn't just store heat statically, it actively moves it around the globe through something called thermohaline circulation, which is often referred to as the global conveyor belt.
So let's break down how that pump actually works. What is physically moving millions of gallons of water across the planet?
It is driven entirely by density, which is controlled by temperature and salinity. So how salty the water is.
Okay, temperature and salt.
Exactly. In the North Atlantic, cold, salty water becomes extremely dense and heavy. It sinks deep into the ocean basin.
Right.
And as it plunges, it creates a massive drawing force, basically pulling warmer surface water from the tropics up to replace it.
So it's pulling warm water north, which dictates regional climates, like keeping northern Europe relatively temperate instead of freezing.
Yes. And that cold, deep water then slowly creeps along the seafloor across the entire globe, eventually warming and rising back to the surface in the Pacific and Indian Oceans.
And how long does that take?
It takes about 1,000 years for a single drop of water to complete the entire circuit.
1,000 years. It's just a colossal, slow-moving planetary air conditioner.
It really is. But it is also acting as a carbon sponge, absorbing roughly a third of all the carbon dioxide we emit.
Right. And there is a massive hidden cost to that. It is soaking up all this CO2, which triggers a process called ocean acidification. I want to really dig into the mechanics of this because it is terrifying.
It is a huge concern.
How does adding carbon dioxide physically harm a crab or a coral reef?
It is basically a chemical chain reaction. When carbon dioxide dissolves into seawater, it forms carbonic acid. This process releases free hydrogen ions into the water.
And why are hydrogen ions a problem?
Because they are highly reactive thieves. Marine life, from massive coral structures to tiny crabs, oysters, and crucial plankton at the base of the food web, they all rely on a molecule called carbonate to build their shells and skeletons.
Okay, so they pull carbon out of the water like microscopic building blocks.
Exactly. But the hydrogen ions steal those blocks. The excess hydrogen ions bond with the free carbonate before the marine animals can get to it. They are literally pulling the building materials right out of the water.
Which forces the animals to expend far more energy just to maintain their shells.
Yes, and if the acidity drops low enough, existing shells can physically begin to dissolve while the animal is still alive.
That is so bleak. I mean, if the plankton at the very foundation of the food web lose the ability to build their shells, the entire structure collapses upward.
It does.
Which makes this final topic we need to cover incredibly tense. Just as we are realizing how heavily our climate stability relies on this fragile deep-sea ecosystem, we're also looking at sparking a massive industrial gold rush at the bottom of the ocean.
Yeah, though it's more accurately a battery rush.
A battery rush, right. Because down on the vast, muddy, abyssal plains of the deep ocean, there are trillions of objects called polymetallic nodules.
Yes, they look almost exactly like dark, charred potatoes just resting on the seafloor.
But those potato-sized lumps, are actually incredibly concentrated clusters of manganese, nickel, cobalt, and rare earth elements.
Which are the exact metals the global economy is utterly desperate for right now.
Because the demand is soaring, right? I mean, if we're going to transition the global energy grid away from fossil fuels, we need millions of electric vehicle batteries, wind turbines, and grid storage systems.
We do. And the metals required for that transition have to come from somewhere. Traditional land-based mining carries a very heavy toll. We're talking deforestation, toxic runoff, and severe human rights abuses.
So mining companies and nations are basically developing technology to bypass land entirely. They want to send massive remote-controlled machines miles down to the seafloor to vacuum up these nodules and pump them to the surface.
Which sounds like a clean solution on paper, but it presents a profoundly difficult dilemma.
Right, and we want to look at both sides impartially here, because the environmental cost in the deep sea is staggering. For starters, those polymetallic nodules do not form quickly.
No, they slowly precipitate out of the seawater over eons. They grow only a few millimeters every million years.
So they are essentially ancient geological artifacts.
They are. And because they are the only hard surfaces on an otherwise muddy plain, they act as the anchor points for an incredibly delicate ecosystem of deep-sea sponges, corals, and unique marine life.
So if you vacuum up the nodules, you strip away the foundation of that entire habitat.
Exactly. And furthermore, you can't just gently pluck them off the bottom. These heavy mining machines have to dredge the seafloor.
Which kicks up massive sediment plumes, right? Like underwater dust storms of mud and disturbed toxins.
Yes, and because there are very few strong currents at that depth to disperse the mud, these plumes can travel for miles beyond the immediate mining site.
Just drifting and settling.
Yeah, and as the sediment slowly settles, it can suffocate the surrounding filter feeders and bury neighboring ecosystems.
Wow.
And remember, life down there operates on such a slow metabolism and long lifespan. Recovering from that kind of industrial disturbance wouldn't take years. It could take centuries, if the ecosystem can recover at all.
So it is a genuine paradox. We desperately need these metals to build the green technology that will mitigate climate change. But to get them, we are considering heavily industrializing the very ocean environment that is currently shielding us from the worst effects of that same climate change.
Yeah, it's a profound irony.
And we are making these decisions about an environment we haven't even finished exploring. I mean, every time an expedition goes down to these abyssal plains, they discover new species.
It's like we're debating whether to strip mine a library before we have even bothered to read the books.
What a fantastic analogy. And, what an absolute journey today. We started by looking at a high-pressure, pitch-black world, assuming it was a barren wasteland.
Right, but instead we found a neon metropolis communicating in flashes of chemical light.
We found ancient, slow-moving creatures waiting for a rain of marine snow. We found superheated volcanic vents where toxic bacteria rewrite the foundational rules of what it means to be alive.
And we uncovered a massive hidden planetary pump of deep currents that absorbs our excess heat, regulates our daily weather, and sits at the absolute center of a complex global debate over our natural resources and our clean energy future.
It really brings everything right back to that startling realization we started with. We truly do possess better maps of the craters of Mars, a dead, frozen desert, than we do of the largest, most critical habitat on our own planet.
A habitat that heavily dictates our very survival.
Exactly. So, for you listening, as you go about your day-to-day, just enjoying the oxygen you breathe and the stable climate you live in, I want to leave you with one final thought to mull over.
I think I know where you're going with this.
Think about the blobfish's cellular proteins surviving under 1,000 atmospheres of pressure. Think about the tube worm thriving in boiling toxic acid. If deep-sea organisms have spent millions of years biochemically adapting to the most extreme, crushing, hostile environments on Earth, what life-saving medicines, revolutionary new materials, or scientific breakthroughs might be hiding right now within their DNA?
It's a huge question.
It is. And the real question is, will we map the ocean floor in time to discover them before they are lost to acidification or industrialization?